Hi, welcome to Trojan Corner. Today we are reading The History of Counting by Denise Schmant-Basserat. The system of counting we use today has one base, 10. In this system, called decimal, after the Latin word for 10, large numbers are multiplications of 10. For example, 10 times 10 equals 100, and 10 times 10 times 10 equals 1,000. While the Sumerian system of counting was remarkable for their time, it did have a drawback. It had no zero. In other words, the Sumerians had no sign to indicate no value. They just left a space. This was unclear and led to difficulties in reading numbers. You can see this for yourself. Look at the number 204,501. How easy is it to write without zeros? 2451? Although the space of the numerals changed, the Sumerians' counting system itself was used for centuries. The Babylonians were still using it 2,000 years later, around 600 BC. Why was such a complicated counting system used for so long? Perhaps because it is easier to follow old ways of thinking than to come up with new ways and innovate. The Phoenicians, who invented the alphabet around 1500 BC, innovated. They used the letters of their alphabet as numerals and had only base 10. The Phoenicians' innovations showed that counting evolved by leaps and bounds. Although we would like to know why, where, and when the alphabet was invented, and how the letters became used as numerals, the memory of such things is lost. We do know that by 500 BC, the Greeks had borrowed the Phoenician system. They used 27 letters of their alphabet as numerals. The first 9 letters were the digits 1 through 9. The next 9 letters were the tens, and the last 9 letters were the hundreds. The last letter stood for 900. The Greek numeral system shows that the people of Athens seldom dealt with more than hundreds in daily life. However, Greek state accountants and mathematicians had a system of writing numerals beyond 900. 1,000 to 9,000 was shown by the sign, the apostrophe, to the upper left of the number. For example, apostrophe A was 1,000. 10,000 to 190,000 was indicated by placing an M, the Greek letter mu, before the numeral. For example, E over mu equals 50,000. The Greek numeral system was troublesome because it used as many as 27 signs. By 200 BC, the Romans improved on it by reducing the number of signs to 7 letters. Once again, the fact that the common numerals did not reach beyond 1,000 indicates how infrequently large numbers were used in everyday life in Rome. But here too, state accountants and mathematicians had a system of expressing high numbers. They added a line over the numeral. So you get a line over V equals 5,000, a line over the X equals 10,000. The Phoenicians, Greeks, and Romans had a limited set of numerals. The highest numeral in the Greek system was 900, and for the Romans it was 1,000. When they needed to count above that, they had to use complex systems of markings. And, following the Phoenicians, the Greeks and the Romans used the base 10, but still, neither of them had 0. The Romans' numeral system depended on place value. This means that the number takes a different value according to its place. In the Roman system, when a small number follows a large one, the two numbers are combined or added together. For instance, xi equals 11. But when a smaller number precedes a larger number, the smaller number is subtracted or taken away from the larger number. So ix is 9. Place value reduces the number of special signs to remember. However, reading Roman numerals still meant adding or subtracting how many ones, fives, tens, and so on were included in the numeral. In Rome, these numerals were used for recording totals, but the actual computing was done with counters on a counting board that had horizontal lines drawn on it. Counting started with large units. Each 1,000 was matched on a counter that was placed at the top line of the counting board, the line standing for 1,000. Then the hundreds was matched to the counters that were placed on the line below, followed by the tens and the units. All the counters were computed together, and the result was recorded with numerals. For example, 2,000, mm, 800, dccc, and 7, VII, was written MMDCCCVII. Roman numerals were still commonly used when Christopher Columbus set sail in 1492, and we still use them occasionally for showing dates on buildings, for numbering volumes and chapters in books, and when indicating hours on some clocks. But when we add, subtract, multiply, and divide, we use digits called Arabic numerals. and we write them as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Where and when the Arabic numerals were invented is a mystery. So is the identity of their inventor. Why then are the digits of our counting system called Arabic numerals? Because it was the Arabs who brought them to Europe and the year AD 1000 when they ruled Spain. The Arabs, however, called these digits Hindu numerals because they had borrowed them from India. The earliest document bearing such numerals was written in the ancient Indian Sanskrit language about 1500 years ago. No one knows how long the system was used before that or what preceded it. The transition from Roman to Arabic numerals took centuries. The Europeans refused to change the old ways, saying, for instance, that the signs for 2 and 3 could be easily confused. Finally, by around 1650, Arabic numerals were finally accepted in Europe, and they still make up the number system today. Arabic numerals make counting and computing far easier than any previous system. Why? The first advantage has to do with the numerals used. There are separate symbols for each of the 10 digits. This means, for example, 3 is no longer the repeated I. 4 was no longer 5 with a subtracted unit, IV. 6 was no longer 5 with an added unit, VI, and so on. The 10 digits 0 to 9 can be used to create numbers indefinitely. On the other hand, the 27 Greek letters reached only to 900, and the 7 Roman numerals to 1000. If people needed to count higher, new signs had to be invented. The second advantage is that the names for the numbers are repeated and so are easy to memorize. Each digit, 0 to 9, has an individual name. 0 is 0, 1 is 1, 2 is 2, counting through 9 is 9. So do multiplications of 10 by 10. 10 times 10 equals 100. 10 times 10 times 10 is 1,000, and so on. The names of all the other numbers are combinations, with the exception of 11 and 12 in English. For example, 20, 21, 201, 2002. This means there are far fewer numbers to remember than the 27 in the Greek system, the 28 in the Palaean body counting method, and the many words for the concrete counting system. The third advantage of Arabic numerals is the better place value. Unlike previous systems, each digit has a variable or different value that depends on the digit is placed. A 4 stands for 4, 40, 400, or 4,000, according to whether it is placed in the first, second, third, or fourth position. Its value does not depend on the value of the digit next to it, as in the Roman system, which is XL means 40, but LX is 60. The same tens digit can be used over and over again to count indefinitely. It is not necessary to have different types of signs to indicate units of tens, hundreds, and so on. The fourth and greatest advantage of the Arabic numeral system is the invention of 0. 0 provided a sign for no unit. In other words, none or no value. Combined with place value, 0 made computing far easier before because, while 0 has no value, it shows clearly the place value of each digit of a number. Plus, it marks the place even where there is no unit. For example, in 1010, 1 at the far left stands for 1,000. 0 to the right stands for no 100. 1 to the right stands for 10. And 0 to the far right stands for no unit. 0 makes it possible to arrange numerals in columns in order to compute them. In other systems, numerals cannot be arranged this way. Look at the simple addition problem. 1,084 plus 1,797. To add the Arabic numerals, you line up the numbers in columns, placing the units below the units to the far right, the tens below the tens to the left of the units, the hundreds below the hundreds to the left of the tens, and so on. Then you add the units, note the number of units, and carry over the tens, and so on. Now try to add the corresponding Roman numerals, MLXXXIV plus MDCCXCVII. Even if you lined up the units, tens, hundreds, and so on in columns, it wouldn't help. 0 makes it possible to go from unit to 10 to 100, and so on, without changing the shape of signs. Compare 1, 10, 100, and 1,000 with I, X, C, and M. The invention of Arabic numerals meant a new system of counting and computing. Most of us take our modern system of counting for granted. We forget or never even realize that counting had to be invented, and that it has been improved upon over a long period of time. In fact, counting was not invented once, but many times. This is why various people around the world have different ways of counting, why some societies make more use of numbers than others, and why some systems of counting are more efficient than others. Counting evolved. In the Middle East, hunters and gatherers counted in a one-to-one relationship around 15,000 BC. Concrete counting coincided with the beginning of farming around 8,000 BC, and abstract numbers were invented in the first cities about 3,000 BC. The invention of abstract numbers was the real starting point of counting. Then bases and place value made the creation of larger and larger numbers possible. Finally, the invention of Arabic numerals with zero made counting limitless and computation simple.